So read the problem once more. A simply supported beam of 4 meter span. Here the beam has 4 meter span and carrying a point load as shown in the figure. So here the loads are shown in the figure and the beam is shown in the figure. Draw the shear force and bending moment diagram for a beam. So simply supported means a reactions at the ends need to be having. So at A and at B, we will need to find out the reactions and the loads. Here a UDL and a point load, both are acting on my beam. So how to consider this? So here, first of all, beginning of the UDL need to be considered 1 point and ending of the UDL need to be considered another point. Therefore, C and D. And at wherever the point load is acting at that point, we need to consider another point. Therefore, here both UDL beginning as well as point load at a C only. Therefore, no need of considering another point. Therefore, I need to consider the equilibrium condition. That is, whatever the forces moving upward direction need to be balanced by the forces moving downward direction. Therefore, here downward direction is 4 kilonewtons and the force UDL need to be converted into force because the UDL have kilonewton per meter, but the reaction forces need to be in only kilonewton. So I need to convert this 2 kilonewton per meter into kilonewton. So I need to multiply with the distance acting of that UDL. So the UDL distance here is 1 meter because both sides have given as 1.5, 1.5. Therefore, adding this 2, we'll get 3. Total length of the span is 4. So 4 minus 3 will getting a 1 meter. So 2 into 1. So again it becomes a 2. Therefore, RA plus RB is equal to 6 kilonewton. This is the first equilibrium condition. And the second equilibrium condition is the sum of the moments at A. The sum of the moments at A. Consider the section at A. Consider the section at A. And consider the moments on my right hand side and forces and its perpendicular distance. Forces and its perpendicular distance. The forces and its perpendicular distance need to be considered. So RP into the distance here 4, RP into 4. Next, a point UDL is converted into 2 into 1. The UDL is converted into point load, that is 2 into 1. And distance from the A. Distance from A is nothing but 1 by 2, 1 by 2. The total length is here, x is nothing but 1 by 2 plus 1.5 is the distance from A. And next, a point load of 4 into distance is 1.5. Due to these two loads, it is moving in clockwise. Due to RB, it is moving in the anti-clockwise. So anti-clockwise taken into the right hand side and clockwise are taken into left hand side. Therefore, we are getting RB value as 2.5 kilonewtons. Substituting in the equation 1, I am getting RA value as 3.5 kilonewtons. After finding RA and RB, I need to draw the shear force diagram and bending moment diagram. I need to draw the shear force diagram and bending moment diagram. So to draw the shear force diagram, I need to move this section. I need to move this section from the right hand side to the left hand side. So the first point is the B. Before B, it is 0. At B, a positive 2.5 kilonewtons. Next, the section is moved to the D. Before D, the same positive 2.5. At a D, a positive 2.5 only exists. a positive 2.5 only exists. Next, before D. Before D means here no need of considering the any point loads, because here only 2.5 is existing at a D, and before D only that point load is existing. Therefore, we will get a positive before. So before D, at a D is same 2.5 mm. Before D also will be before D. So before D and at a D, this is before C. Sorry. So before C, so no point load need not to be considered. Before C, no need of considering a point load. Therefore, a UDL 2 into 1 need to be considered here. 2 into 1 need to be considered here. Yet C, the point load also need to be considered. The point load also need to be considered. Therefore, -4 need to be considered here, which is moving downward direction, Therefore, -4 need to be considered here. So we are getting a -3.5 kilonewton. And last point is A. Before A means whatever the forces on my right hand side, no need of considering 3.5 kilonewtons. 3.5 kilonewtons matram consider cheyakoకుండా ఈ టైప్ సైడ్ మొత్తం అంతా కన్సిడర్ చేయాలమ్మా. So I am getting a -3.5 kilonewtons. Yet A, I need to consider the positive 3.5 also now. So 2.5, 2 into 1 and -4 and positive 3.5, that gives us 0 kilonewton. So now using all these values, I need to draw the shear force diagram. So I am getting the values of 0 first, and next a positive 2.5, and again a positive 2.5, and again a positive 2.5, and next a positive 0.5, next I am getting a negative 3.5, and again 0.5, again 0. So here I need to join all this. So here I will get a horizontal line, and wherever the UDL is existing, I will get inclined straight line for the shear force diagram. Therefore, here 4 kilonewtons external load is applied. Therefore, I will get a vertical line downward direction. Next, a horizontal line. Again, I have 3.5 moving upwards. Therefore, a vertical line need to be exist. Therefore, I am getting the shear force diagram like this. It is also changing the sign. But the location is a known location now. The location is the known location. The location నాకు తెలుసమ్మా. So already C, at C only it is changing its sign. Therefore, I will get a maximum bending moment at C. The maximum bending moment will be occur at C. Now, taking the bending moments, diagram. So the section is at B now. The section is at B. Therefore, force into perpendicular distance is 0. It is passing through B. Next, the section shifted to D. The section shifted to D. Therefore, the force are 2.5 and the distance here is the distance. 1.5 is the distance. So I am getting this value. Next, the section is shifted to the C. The section is shifted to the C. Therefore, I am getting 2.5 is the force and the distance from the C is 1 plus 1.5. It is nothing but 2.5. This is 1. So 1.5, I am getting 2.5 meters as the distance, and a UDL 2 into 1 is converted UDL is there. So 2 into 1, and the distance from the C, the converted UDL distance from the C is 1/2. Since the 1 is the length of the UDL and the distance will be half of its length. So it is 1/2. Next point load is the 4 kilonewtons. Next point load is the 4 kilonewtons. 4 into, it is passing through C. Therefore, the 0. Therefore, it is a 0. So I am getting this value. Next, at A, therefore 2.5 and the distance is 4. Next, UDL, that is 2 into 1. The distance is 1/2 plus 1.5 is the distance from A. Next, another point load of 4 kilonewtons, 4, and the distance is 1.5. So I need to get a 0. And using this, I need to draw the bending moment diagram. So if you observe here, the UDL is acting in between C and D. So by a free hand, I need to join this. So other than that, I need to join by a straight line. So we are getting a positive bending moment diagram. I am getting a positive bending moment diagram. Next problem. A simply supported beam of AB 6 meters long is loaded as shown in the figure. So if you observe here, two UDLs are acting. Two UDLs are acting here, and another point load is acting here. And I need to find out the RA and RB reaction forces at the supports. So this UDL need to be converted into point load. So 4 and its distance is 1.5. The UDL acting distance is 1.5. So that is the 1 point load, converted point load. And next, 2 kilonewtons per meter and its distance is 3 meters. So another point load W2, 2 into 3 is another point load. And it acts at a distance of the center of the 3 meters. That means the same location. Wherever the 5 kilonewtons is acting, the same location will be a W2 value. The same position will be the W2 value. Therefore, considering the forces in equilibrium condition, therefore RA plus RB is equal to 4 into 1.5. 4 into 1.5, this is the point load, and another individual point load, and UDL converted point load 2 into 3. So this is the RA plus RB value. That is the first equation considering the forces in equilibrium condition. And next, considering the bending moments, considering the bending moments at A, considering the bending moments at A. So RB into the distance is 6. RB into the distance is 6. Next, point load is a 5. Point load is a 5 kilonewtons, and its distance from A. Its distance from A is 4.5. Its distance from A is 4.5. Since the total length of the span is 6 meters and 5 kilonewtons is acting at 1.5 distance from B. Therefore, the remaining length is 6 minus 1.5. 6 minus 1.5. Therefore, I am getting 4.5. Six minus 1.5, I am getting 4.5 meters. Next, a UDL converted point load 2 into 3, and its distance from A, the same 4.5, because both loads are acting at the same distance, same position. Next, a UDL converted into point load 4 into 1.5, and its distance from the A is 1.5 divided by 2. 1.5 divided by 2, because at the center it need to be having. At the center it need to be having, therefore 1.5 by 2. So using this, find RA and RB. Using these equations, find RA and RB. So here RB is 9 kilonewtons. The answer will be RB 9 kilonewtons and RA is 8 kilonewtons. The procedure will be same, Amma. The procedure will be same. Each and every point need to be considered. So first point is B, second point is E, and third point is D, and fourth point is C, and fifth point is A. Fifth point is A. So before B is 0, yet B is 9, a positive value. Now I need to consider the E point. I need to consider the E point before E. So UDL will be existing here. Whose length of the UDL is 1.5. Therefore, I need to convert this UDL into again a point load whose magnitude is 2 into 1.5. 2 into 1.5 before E. The section is before E. So 2 point loads, that is 9 kilonewtons, and 2 into 1.5, 2 into 1.5, that is 3. So I am getting a positive 6 kilonewtons. Next, yet E, a point load of 5 is also need to be considered now, which is moving downwards. Therefore a negative. So here another point load of 5 kilonewtons need to be considered. Therefore we have 3 point loads, one converted UDL and this point load. So 3 point load is existing. Therefore one is 9 and a UDL and another, that is 5. So total I am getting a positive 1 kilonewton. Next point is D. Next point is the D. Therefore, the section need to be having at the D. The section need to be having at the D. Therefore, the total UDL length now is again 3 meters. The total UDL length is again 3 meters. Again 3 meters. Therefore, 5, that is 9 is upwards and 5 is downwards, and UDL 2 into 3. 2 is the magnitude, 2 is the magnitude, and 3 is the length of the UDL. 3 is the length of the UDL. So 2 into 3 need to be considered now. So I am getting a minus 1 kilonewton, minus 2 kilonewton as the value at the D. Same, because there is no point load is in at D, therefore the same value will exist. Next point is C. Next point is C. Therefore the shear force before C, there is no load in between B and C and D. Therefore the same value will exist. At C also will be having the same load. Next, before A, next point is A. Therefore 9 is the first load and 5 is the second load, and 2 into 3 is the third load, and a UDL of 4 into 1.5 is the fourth load. So I am getting a minus 8 kilonewton. Yet a positive 8 kilonewtons also need to be considered. Therefore, I will get a 0 kilonewtons. 0 kilonewtons. Using this, I need to draw the shear force diagram. Using this, I need to draw the shear force diagram. So initially it is a 9, a positive. So I am getting this point. And next, another point, and 5 is reduced. Again, I am getting a positive only. At a D, I am getting a negative. And it is followed up to here. And next, a negative H and 0. So here, the sign change, a positive shear force to a negative shear force, occur at unknown location. The sign change occur at the unknown location. So if you see here, there is a straight line only, but it is an incline because a UDL is existing in between A and C. And a UDL is existing between D and B also. So inclined straight line. And a point load is also exist here. So we are getting a vertical straight line in between also. Majlo vertical line kuda vastundam indutlo because a point load is existing here in between. So I need to find out this location. So I am considering this as M point. I am considering this as a M point. Therefore, the shear force at M is equal to 0 from the graph because it touches the baseline. It touches the baseline. That means it is a 0. That means it is a 0. Therefore, I am considering the section at M. I am considering the section at M. Therefore, the loads, the section is now M. The loads are first 9 kilonewtons moving upwards, and we have a 5 kilonewton, that is a point load, and an entire length UDL. I don't know this length, entire length as a UDL. I know this length, 1.5. Therefore, I consider from E as X. From E kandi X anukunnanamma. I know this distance 1.5. Therefore, 9 kilonewtons directly taken as a positive. Next, a 5 kilonewtons point load. A 5 kilonewtons point load moving downwards. Therefore, it is a negative. Next, a UDL need to convert into point load. UDL need to be converted into point load. That is 2 into the distance is 1.5 plus X is the distance. 1.5 in plus X is the distance in meters. Therefore, substituting in my equations, I got that X is equal to 0.5. That means the distance from E to M, E to M is 0.5 meters. I have considered this X as E to M. From E to M as X. Therefore, I got this value as 0.5. So I will get a maximum bending moment at M. The maximum bending moment at M, I will get the maximum bending moment. So while drawing the bending moment diagram, I need to consider the M point also. So here I need to draw the bending moment diagram. So bending moment diagram at B, because there is no perpendicular distance, 9 into 0 becomes 0 again. So directly 0. And E, at E, so here some UDL is acting here. Some UDL is acting here whose length is 1.5. Therefore 9 into the distance is 1.5 because at E, B to E, the distance is 1.5. B to E, the distance is 1.5. And the UDL length here is 1.5. So 2 into 1.5. 2 into 1.5. And next, the distance of the UDL from the E is 1.5 divided by 2. This is the distance. So I am getting this value. Next, I need a section at M. That is a maximum bending. That is the maximum bending. So, what is the distance of this? The distance here is, I got 0.5 from E to M and again 1.5 is existing here. Therefore, the total distance is from M to B is 2 meters. M kandi B daka distance. Nakemo idi 0.5 vachindama. This is 0.5. This is 1.5. Therefore, I am getting a 2 meters as a total distance. Therefore, 9 into distance is 2 from M. And the UDL, converted UDL, the distance here is 2 meters again. Therefore, 2 into 2. 2 into 2 is the point load and the distance is 2 by 2. The distance is 2 by 2. The distance is 2 by 2. And next, one point load of 5 kilonewtons, his distance from M is 0.5. So I am getting a positive 11.5 kilonewton meter. Next, I need to shift for the D. I need to shift for the D point. The section is shifted for the D point. Therefore, 9 into the distance is 3 meters and 2 into 3. The length of the UDL now here is 3 meters. The length of the UDL is 3 meters. So 2 into 3, and the distance will be 3 by 2. The distance will be 3 by 2. And next, 5 is the point load, and its distance from the D is 1.5. From the D is 1.5. Therefore, I am getting the value of 10.5 kilonewton meter. Next, I shift the section at C. Now the section is at C. Therefore, the distance of 9 kilonewtons from the C. ఈ 9 కిలోన్యూటన్లో C కాండి ఎంత డిస్టెన్స్ లో ఉందో కావాలి నాకు. So here the total length of the beam is 6 meters. So here 1.5, the remaining is 4.5. 9 into 4.5 meters. 9 into 4.5 meters, and the UDL length is here only 3 meters. The UDL length is only 3 meters. So 2 into 3 is the point load. 2 into 3 is the point load, and 3 by 2, it acts at the center, that is 3 by 2 is the point load acting location. And from the C, the length is 3 by 2 plus this length is 1.5 again. 1.5. Therefore, 3 by 2 plus 1.5. So I am getting this length as a 3 meters. This length as a 3 meters. Again a 5 kilonewtons into a 3 meters again. So I am getting a positive 7.5 kilonewton. The bending moment at A need to be at 0. The bending moment at A need to be at 0. Using all these points, I need to draw the bending moment diagram. Using all these points, I need to draw the bending moment diagram. And while drawing also, you need to observe the UDL positions. So in between D and B, so this is the D point and this is the B point. So in between D and B, the UDL exists. Therefore, I need to join all this by free hand. Next, in between A and C also UDL exists. So this is also free hand. So remaining C and D, the remaining C and D need to be joined by a straight line using a scale. Okay, Nama? Next, very important. The procedure is same, Amma. The procedure will be same. The difference is only the beam is changed. The procedure will be same. Only the beam is changed. Now I am considering a simply supported beam with uniformly varying load. So here the variation is uniformly varying load. And we'll have reaction forces and RA and RB. RA and RB will be existing here. So I need to convert this UDL, that is uniformly varying load, into a point load of W. So it looks like a triangle. The area of the triangle is half, base is L, and length, that is height is small w. That is the capital W value. That is the point load. I converted this into point load, and it will be acting at a distance of L by 3 from the right angle. It will be acting at a distance of L by 3. That is, it must be passing from the centroid. It need to be passed from the centroid. Therefore, it is at a distance of L by 3 from the right angle, and from the apex, the point load distance is 2L by 3. 2L by 3. Now I have converted this into 3 point loads, RA, RB, another point load capital W, and its distance. Now RA plus RB is equal to capital W, because RA is moving upward direction and RB is moving upward direction. The downward direction is capital W. The W, capital W, is nothing but half small w into L. And the bending moments at A, now. Therefore, RB into distance is L. RB into distance is L from A. Therefore, RB into L, and point load, that is the capital W, and its distance from A is L by 3. It must be equal to 0. The bending moments at A is equal to 0. Therefore, substituting the capital W value, I will get small w L square by 6 is equal to 0. Therefore, RB is equal to small w L by 6. Therefore, substituting the RB value in my equation 1, RA will be small w L by 3. So now I know this RA and RB. I know the RA and RB. I need to find out the shear force diagram by using the formula. So now I need to consider a section. I need to consider a section at a distance of small x from the B point. Therefore, the height at that position is not known. The height of that position is not known. So to find this, I need to use the similar triangles. Tan theta, this is the theta value ma. Tan theta for the big triangle is W is the opposite side and L is the adjacent side. Therefore, W by L we are getting for the big triangle. And for the small triangle, the same tan theta is equal to, here opposite side is Y and the adjacent side is X. Opposite side is Y and adjacent side is X. Therefore, Y by X. Here angle will be same. Therefore, tan theta will be same for the both. So Y will be W into X by L in terms of X. Y in terms of X. Now, I am considering a section at XX at a distance of small x, and I am considering a small triangle. I need to convert this into point load again. Therefore, here the area of the small triangle is half, base is x and height of the triangle is the y. Half x into y is the area of the triangle. Therefore, substituting the y value, I will get capital W in terms of small w x square by 2L. Small w x square by 2L. Therefore, the shear force at XX is equal to, we have two forces, RB and capital W. Only two forces are existing. Therefore, RB is moving upward direction, so it is a positive, and W is moving downward direction, so it is a negative. Therefore, substituting RB value and W value, I am getting a relation. Now, to draw the shear force diagram, I need to substitute x is equal to 0, x is equal to 1, x is equal to 2, x is equal to 3, and so on, x is equal to L. In this, my standard equation. I need to substitute the values of x. That is, the section is 0 means at B. X is equal to 0 means at B. X is equal to L means at A. The section will be moving in this direction. And I will get the shear force values. Now, I need to draw the bending moment diagram. To draw the bending moment diagram, I need the forces and the distance. Of that forces from my section. Now the section is XX. I need the distance from my section. Therefore, this is the first force, RB, and it is at a distance of X from my section. So this is the distance. This is the force. Next load is W. It is acting at a distance of X by 3. Therefore, substituting RB value and W values, we will get a standard equation. After that, I need to substitute x is equal to 0, x is equal to 1, x is equal to 2, x is equal to 3, so on, x is equal to L. That is, x is equal to 0 means at the B, x is equal to L means at A. So I will get the bending moment values while varying the x values. Using these values, I need to draw the shear force diagram and a bending moment diagram. Using these values, I need to draw the shear force diagram and a bending moment diagram. Since if you see the shear force diagram equation, it is a squaric equation. Y, shear force is nothing but y is equal to in terms of x and in constants. So we will get a freehand curve. And we also get a freehand curve. So if you see observe the shear force diagram, it changes its sign. From positive to negative or negative to positive. I know the location, therefore find the x. So in this equation, in the shear force equation, shear force is equal to 0, find the x. Considering the shear force is equal to 0, find the x. That is nothing but a x value. At that location only, I am getting a maximum bending. At that location only, I am getting the maximum bending. Therefore, at that point also, I need to find out the bending moment. Amma, this is a diagram. This point will be a positive points and this will be a negative points. This all will be a negative points. This all will be positive points. Since I have considered the upward forces as a positive and downward forces as a negative, so initially it must be positive and the curve must be like this. Some textbooks look like this. మనం కన్సిడర్ చేసేదాన్ని బట్టి ఉంటుందమ్మా. మీరు ఇనిషియల్గా ఏది అయితే కన్సిడర్ చేసుకున్నారో అలాగే ఫాలో అవ్వాలి. డు నాట్ కన్ఫ్యూజ్ అవ్వకూడదు మీరు. One textbook will be shown in this direction, one textbook will be shown another direction. The bending movements ఏ టెక్స్ట్ అయినా సేమ్ ఉంటుందమ్మా. షియర్ ఫోర్స్ డయాగ్రామ్ మాత్రమే ఆపోజిట్ డైరెక్షన్స్ లో వస్తాయి కొన్ని టెక్స్ట్ బుక్స్ లో. సో నీడ్ టు బి కన్సిడర్ పర్ఫెక్ట్లీ while drawing the diagram. So 3 types of loads is completed now. Point load and UDL as well as varying load. Another important question here is a trapezoidal load. Trapezoidal load on my simply supported beam. Trapezoidal load on my simply supported beam. So this is another important question. The procedure will be same. The procedure will be same, amma. I need to convert this into a rectangle as well as triangle. So a rectangle whose magnitude is 800 into the length is 6. And the triangle, the remaining 800 lonely 2800 తీసేస్తే triangle height will be 1200. Triangle height will be 1200. Therefore the base will be 6 again. Therefore half into 1200 into 6 is the point load while the triangle load. The rectangle load కేమో సెంటర్ లో యాక్ట్ అవుతుంటుంది L/2 డిస్టెన్స్ లో. ట్రయాంగులర్ లోడ్ ఏమో L/3 డిస్టెన్స్ లో యాక్ట్ అవుతుంది కాబట్టి 6/3 we are getting a 2 meters and 6/2 I am getting a 3 meters. Now the problem is converted into only 4 point loads RA, RB, W1 and W2. So I can find the RA and RB now. I can find the RA and RB now by using the same procedure. After finding RA and RB, I need to consider a section. I need to consider a section XX at a distance of small x. Now similar process again in the small section meda I will get W1 800 into x and W2 will be half into x into y. X is the base and y is the height of this triangle. Therefore area of the small triangle is half W into x. Therefore పెద్ద triangle తీసుకుంటే 1200 by 6 చిన్న triangle తీసుకుంటే y by x. Therefore y is equal to 1200 by 6 into x. Y will be 1200 by 6 into x. Now 2 point loads, that is 3 point loads are existing. So I can write the equation. Shear force at any location is equal to RB is the first load which is moving upward direction and W1 which is the moving downward direction. So a negative, and W2 is nothing but a force due to triangular force which is moving downward direction. Therefore, this is the equation attaining at any section. Now substitute x is equal to 0, x is equal to 1, and x is equal to 2, x is equal to 3, x is equal to 4, x is equal to 5, and x is equal to 6 is the last. Length of the span is 6. Now find all the values. Find all the values and shear force values at each and every point by substituting x is equal to 0, x is equal to 1, x is equal to 2 in my standard equation. I will get the shear force values. And bending moments. The bending moments. So three forces here. RB, its distance is x. RB, its distance is x, is the first force. And the second force is W1, and its distance is x by 2. And next, W2, its distance is x by 3. So substituting RB, W1 and W2 and getting the bending moment equation, standard equation, substitute x is equal to 0, x is equal to 1, x is equal to 2, x is equal to 3, x is equal to 4, x is equal to 5, x is equal to 6 is the last. So while substituting, I will get the bending moment diagram as well as shear force diagram like this. Here the shear force diagram will be positive, it will be positive beginning. It will be ending at the negative in opposite directions, vice versa. It will be opposite direction, it will be negative, it will be positive. So with this, I am concluding this section. So only a couple. So a shear force diagram with a overhanging beam is left here. Overhanging beam is left.